Hi everyone, thank you for joining us today. We'll wait for 2 more minutes and then we'll start the program.
Hi, Dan. Thanks for agreeing to do this. I guess we'll just get started in a couple of minutes.
Okay.
Hi everyone, thanks for joining us today. Professor Gop Kumar, I invite you to welcome the speaker and take it from here.
Okay. Thanks, Gayatri, for organizing this, and welcome to this Vigyan Adda, which is one of ICTS's outreach activities aimed at a broad audience, but often undergraduate students in science and engineering who are interested in some of the cutting edge topics. And I think we can't have a more exciting topic than the one of today, the promise of ultra-cold atoms as a basis for multiple aspects of quantum technology, as you will hear. And we have a great speaker. Professor Dan Stamper-Kurn is a professor of physics at Berkeley, at the University of California, Berkeley, and also a staff scientist, a faculty scientist at the Material Science Division of the Lawrence Berkeley National Laboratory. He earned his PhD from MIT, working with Nobel laureate Wolfgang Ketterle, who was one of the pioneers of this in the subject of ultra cold atoms. I think perhaps many of you have heard of the Nobel Prize winning work on the Bose-Einstein condensation, realizing it in cold atoms. Dan worked with Wolfgang on these pioneering early experiments on Bose-Einstein condensation, and then after postdoctoral research at Caltech with Jeff Kimball on cavity QED, he has established his own research program at Berkeley, and his research touches upon many topics, and we heard some in the program that is happening. So Dan is visiting ICTS as part of our program on ultra cold atoms and related topics, and he had given a technical talk yesterday there, another one at RRI, and he's touched upon many topics in his research that includes magnetic order in spinor Bose-Einstein condensates, cavity optomechanics, quantum limited and mid-circuit measurement, geometric effects in materials, and quantum optics with atom tweezer arrays. I'm sure some of that will enter in the talk today. He has established and now directs a very unique institution within Berkeley, the Challenge Institute for Quantum Computation, which is funded by the National Science Foundation of the US and has grown to be one of the leading academic centers for quantum information science and engineering. Dan has a number of recognitions, including being the fellow of the American Physical Society, Optica, as well as the AAAS, the American Association for the Advancement of Science. He's the co-recipient of the NASA Group Achievement Award for leadership in developing quantum technologies in space. And that's, I think, probably another topic of interest in India, particular interest in India. And also the recent recipient of the 2025 Senior BEC, I presume, Bose-Einstein Condensation Award. So I'll now hand it over to Dan to take us through to the potential future of ultra-cold atoms. Thank you.
Okay, thank you. Thanks, Rajesh. Thanks to everybody who's organizing this great outreach program, and really everybody who's been a really tremendous host here at the ICTS. So I'm happy to be here, and I'm happy to give this lecture. So as you know, quantum mechanics is an old theory. The first mentions of quantum mechanics as a theory came out actually in 1924, so already 102 years ago. But in spite of that, there's a lot of sort of rejuvenated excitement about quantum mechanics, because we now have this newfound understanding that there's aspects of quantum mechanics that may be the bases of future technologies that have a really wide range of applications and may influence society, humanity, in a very big way. So I got really excited about the prospect of, a quantum future for technology. So I went on to Amazon, which is this online store in the United States, at least, and I figured I'd order a bunch of quantum technology. And so it came in a box. It cost $20 or something. I probably paid more for shipping than for the item that actually I received. And so when this box arrived at my house, I was really excited to open it up and view the new quantum technologies. And when I opened it up, this is what I saw. Okay, so that was disappointing. But actually, in this box, if I look a little bit more closely, I realized that there's something floating around inside the box. There were some atoms and molecules in the air that is inside this box. And so I built a very specialized microscope which peered into this box, and I also sent some laser beams into the box that was supposed to scatter off of a particular atom. In this case, it's rubidium-87. And lo and behold, there was my quantum technology. It indeed came in the box. I was very excited about it. Okay, so that's obviously not a real story. But here's the real story. The real story is that atoms in the gas phase may indeed be the center of these quantum technologies that everybody is talking about. And there's experiments that are coming online where we've learned how to trap single atoms in vapor, actually in a very low pressure vacuum chamber, and hold on to single atoms, manipulate them, get them to interact, and measure each and every single atom in a very high fidelity manner. So here's an image that was actually taken in my laboratory already a couple of years ago, which is of a string of traps. I'll talk about this in a few slides. A string of traps. Each of these boxes is a separate place where we might store an atom. And when we send this off-resonance light at these atoms, they scatter this light. And using a not very fancy camera, and in fact, probably even using just your bare eyes, you can see these single atoms glow at these locations. You see where these single dots appear. Each one of these is a single atom of rubidium-87. It really is kind of a shocking reality that you can see single atoms in this way. And these single atoms are all identical. They're all exactly rubidium-87. It's the same isotope. So they all have perfectly calibrated identical properties. We don't have to do any fancy nanofabrication to make them more reliable in their properties. These atoms never go away. They're incredibly cheap. And it may be, in fact, that because we've learned how to control these atoms with such incredible precision, that they can be the stuff of a wide range of quantum technologies. And this reality is built on a lot of years of the development of this field of ultra-cold neutral atomic gases. This is built on the basis of a lot of basic atomic, molecular, and optical physics, or what's known as AMO physics, where for many years we learned how to control the internal states of atoms and observe narrow resonances and establish things like frequency standards for the microwave atomic clocks that are so common, that are floating around in space and are the basis of the global positioning system. But then added to that, there's a lot more where we've learned also how to control not just the internal states of atoms, but as you saw in that previous slide, we can control the motional states of atoms and get them to essentially come to rest in particular locations of our choosing inside of a ultra-high vacuum chamber. And so a lot of developments went into that. Many of these were sort of developed in the years right before I started my own PhD in the subject. And there's actually still, I want to point out, a lot of room for innovation and improvement. For example, that picture I showed you earlier, which is using these things called optical tweezers, that's a methodology that's only really appeared in the last 9 or so years or 10 years. So there's a lot of innovations that are still happening. Anyhow, with this sort of basis, what we've allowed ourselves to do is control, or where we've arrived at is to control the states of single atoms and atomic gases to a great degree. And this field with this level of control has really flourished, and I've been really happy to be part of this field for the last 3 decades of my career, because on each of these branches, there's a really new science that's coming out. So with the same basic methods, you can study ultra-cold materials like superfluids that we produce in a laboratory, in a vacuum chamber, and can study. You can build sensors of exquisite precision where you have atoms that are acting as local sensors, and they're very immune to noise that might disturb the sensor. We've done a lot of research in my lab, but actually across the entire community, to study new aspects of few body physics, including things like ultra-cold chemistry. What happens to chemistry when you enter a zero temperature regime for reactions? Among the scientific directions that are really quite new and exciting is this newfound access to quantum systems that are driven very far out of equilibrium in a way that in solid state matter, it's very hard to do. Solid state systems are very close to their thermal equilibrium, even if we kick them very hard. But these atomic systems can sort of explore the excited state space of a many-body quantum system, and we're making discoveries by looking at them. And then there's also, and I'll touch on this, there's also the prospect of building quantum information processors, that is, quantum computers that are based on ultra-cold atoms. And so it's sort of a giving tree. You know, it's a gift that we've received, and it just keeps giving. There's more and more research and more experimental developments that are coming out from this basic capability of manipulating atoms and also molecules to this degree. Now, as you perhaps know, with this excitement about the future quantum technologies coming our way, there's a range of different technologies that people have considered. So here's a nice slide from the European Commission that sort of exemplifies that there's 4, pillars of applications of these novel technologies. And it turns out that ultra-cold atoms can serve really to advance all of these different applications of quantum information science. And this includes, I'll talk about these 4 topics: quantum simulations, and I'll talk about quantum simulation of materials briefly. It includes novel sensors. In fact, the most sensitive measurement devices we have at present are based on ultra-cold atoms and how they can measure time. It also, as I pointed out earlier, can be the basis of building a quantum computer. And this is a really dramatic development in just the last, let's say, couple of years that it's really had a breakthrough moment that you should know about. And then also the basis of quantum communication, how to send information secretly from one place to another, or with high efficiency from one place to another. And so cold atoms can play a role really in all these directions of quantum information science. So I'll go through these 4 examples. I'll wrap up with some statements about collective effort centers that can be established to advance this field. All right, so let's talk about the first topic, which is quantum simulation. And I like to think of quantum simulation in the following manner. So let's consider condensed matter physics, the study of materials. And the standard approach to material science or condensed matter physics is sort of a dialectic between experimentalists and theorists. The experimentalists find some flake of something in the ground or underground or in a river or whatever, maybe in a laboratory, and they then make measurements on it. And they get some phenomenology that they'd like to understand. So they hand this information over to a bunch of theorists. And the theorists sort of dream, they try to simplify what's happening inside this material because it's really too complicated to fully describe. But they try to describe some minimal models and then run these models, maybe run a numerical simulation, and see whether they can match the properties of materials. Or sometimes actually the dialectic goes the other way. Sometimes theorists actually first dream up some concept of materials and they challenge the experimentalists to create some material that shows what the theorists have been thinking about. A quantum simulator is sort of a third leg in this discussion. And the idea here is that you'll make in the laboratory something that directly simulates something that you think is happening inside of a material, but might be hard for you to make sensitive measurements on. Or maybe something that directly simulates something that is going on inside the head of one of these theorists, but now creates it in a real kind of experimental system where, because of very accessible time scales, length scales, and so forth, you can actually make very detailed measurements that can, for example, take the place of a numerical computation, because after all, any phenomenology you see in this simulacrum of the theoretical idea is essentially the prediction of what this model will do when it runs forward in time. So that's something that quantum simulation brings to the game. And one of the big directions that people have followed in the area of quantum simulation is to simulate the properties of solids, where electrons move around inside of an ionic crystal. Instead, with looking at the motion of atoms, heavy atoms, 10,000 times heavier than electrons, but nevertheless, we can have them move around inside of periodic potentials that we establish using laser light, and these things called optical lattices. And these atoms run around and behave a little bit like the electrons inside of material and give us insight on how materials operate. So this is something that I mentioned yesterday at the ICTS meeting where I spoke. I was pointing out that many aspects of materials, for example, two-dimensional materials, but also really all materials, are based very closely on their band structures. And if we can create experimental systems with our cold atoms and optical lattices that have the same band structures as interesting materials that we'd like to understand better, then maybe studying our atomic system can give us insight on what might happen in a condensed matter system, either that exists or that can be designed based on what the quantum simulator has told us. So we have to make periodic structures that look like the periodic structures of ions inside of crystals. And in many labs, and mine included, we do so by sending in coherent laser beams. And at the intersection of these laser beams, we get periodic intensity patterns, right? The interference of a bunch of plane waves is a spatially modulated intensity of light. And atoms respond to that spatially modulated intensity of light, looking at it, to them, it looks like a potential that they're moving in. So the light is like a crystal and the atoms are like electrons. They move inside of this crystal. In my own lab, we work with optical lattices, these intersections of various laser beams, and we sometimes use two different colors, so two different wavelengths of light that have this 2-to-1 wavelength ratio, in order to make really interesting optical lattices, which look like very interesting solid state systems. So for example, if I just take that green light that was on the previous image and I intersect 3 beams, they intersect in a plane, they all come in at 120 degrees from one another, then they make this intensity pattern that's shown here, which is a triangular pattern in which the intensity goes to 0, surrounded by regions where the intensity is not 0. And it turns out that for the atoms that we work with in my lab, rubidium and potassium atoms in this case, this light at 532 nanometer wavelength is like a repulsive potential to the atoms. The atoms would like to be in the darkest space. They'd like to move out of the bright spots inside of this pattern. So they move to spots that are shown here by these letters, the dark spots. And these dark spots are arranged, you notice, like a triangular lattice. So the atoms moving around in this kind of optical crystal look like electrons that move around in triangular crystal structures. We can add more light. So for example, if we add the red detuned light, so we add light at 1064 nanometer wavelength, and that is below the resonance frequency of the atoms we're working with. So again, there's this intensity pattern. It's twice as big as before because the wavelengths just doubled. And now it turns out that the spot of zero intensity is actually relatively a high energy point because the atoms are attracted to the really bright spots in this pattern. And now if we overlap these two colors on top of one another, let me show you what happens. We can make it so of these 4 sites that I put inside of a unit cell that all were equivalent to one another when we had only the green light, now they're inequivalent to one another because one of them, I've labeled it as site D, is relatively raised in energy. And the sites that remain, you've noticed they have these triangular plaquettes, these ABC plaquettes, and they share vertices with one another. And that creates an interesting crystal structure, something called the Kagome lattice, which in condensed matter physics is a very famous lattice for studying geometric frustration. So using this kind of method, we can make a variety of optical lattices, including lattices that show geometric frustration. We can look at geometric features of these lattices, and that's something that I covered in the talk yesterday. We can look at how the states of particles in a periodic potential vary as you go around the location of two places where a place where two bands touch each other. And by looking at how atoms transported through that touching point, how their populations vary, we have new information on what is the structure of how the states are identified in the lower and the upper band around this band touching point. So, there's a lot of nice research connected to this, which is studying all sorts of aspects of crystals. But then there's even fancier instruments than what I showed you earlier. There are these wonderful instruments that have been around since the late 2000s called quantum gas microscopes. These are really cool things. So basically, you make an optical lattice that's shown by these laser beams that intersect inside of a vacuum chamber. And then you just bring up a very high numerical aperture lens to look down at that optical lattice. And if the lens is a high enough quality, and sometimes you can just buy them off the shelf, sometimes you have to design them yourself, then they can actually resolve one site of the optical lattice from the other. And if you have atoms inside of that optical lattice and you shine near resonant light on them, which they scatter, then you get a bright dot at the location of each atom. And now inside of this crystal made of light, you can see in a snapshot where every single atom is located inside of the crystal. So this is a fantastic development that's led to really a lot of wonderful science. And most recently, actually, in a real breakthrough that happened just last year, people have learned how to make the gases inside of these quantum gas microscopes very much colder. Okay, so this was a breakthrough in the work in the group of Marcus Greiner at Harvard University, and kind of came up with this idea for how to first put atoms in a lattice that had few sites, and then adiabatically transfer it into or transition the system into a lattice that has many sites. And in doing so, they sort of keep the gas very, very cold, but allow more physics to happen. And the physics that should happen is summarized by this diagram over here. Something that this group and many others have been studying for a long time is something called the Fermi-Hubbard model, a model where you have fermions that move around in a lattice, fermions like electrons, and they have just on-site interactions. So if two fermions come onto the same site in the crystal, then they repel one another. And there's been a huge question in the theoretical and experimental community for the last 40 years of whether the Fermi-Hubbard model, when you get a system cold enough under this model, and also you add doping, so you either add extra particles or you take away some particles, whether it realizes D-wave superconductivity. It's supposed to be a theory that might explain how high TC superconductors work. And really, just as of this year, there are finally experiments that are peering into this very low temperature or low entropy region in this phase diagram and may very soon give us this long-awaited answer of whether the Fermi-Hubbard model supports superconductivity. So that's really super exciting. Now, there might be questions, and one of the questions which haven't been asked of me yet is, really, this does not sound like a technology to me. This sounds like experiments. And I want to make an argument that, in fact, quantum simulation might be one of the most important applications of this new brand of quantum devices. Because I think it can be argued that humanity desperately needs to overhaul our most essential technologies, because we face like at least three very pressing, essentially existential questions all at once. We have understood that the way we produce energy is spoiling our planet. And if we want to keep building, developing, and advancing as a species, we need all that energy. So we need to find a new way to make energy that is not so problematic for us. We also need to develop the standard of living worldwide. There's a lot of folks around, and people should live, comfortable, decent lives. And so we need to keep pushing down the poverty rate and improving the standard of living worldwide. That requires a lot of development, and that's going to impact our planet, but also it's something we need to do in a hurry. And then we also face this like really looming problem that energy is in very high demand. This is actually an old slide which didn't realize that artificial intelligence was going to completely break this curve, and we just need to make more and more energy. We need to process more and more information, let's say in these artificial intelligent or machine language systems, without creating so much energy, because we just don't have that much energy around. So there's really big pressing problems, and arguably within just a few decades, we have to change almost all of our essential technologies if we're going to keep developing at the rate we have while doing so sustainably. And if quantum simulators, in the kind of experiments that I told you about, can accelerate materials research, they're delivering something that's of enormous value and need for humanity. So that's a really important aspect for these technologies to achieve. Okay, so that's quantum simulation. Let me move on to other applications of ultracold atoms, and this one is in the area of quantum sensing. So we want to build quantum-based devices that can measure the natural world ever better, and this has applications, both fundamental scientific applications, but also very applied applications or technological applications. One of the most sensitive measurement devices that we as people have ever made is the optical atomic clock. And so I didn't have a slide that explains this very clearly, but there are optical transitions in many atoms where the transition is at a high energy, so a high frequency, but where the ground and excited state are very long-lived, so it's actually a very narrow resonance. And because of that, you can actually keep time very precisely. A superposition in these two levels will sort of tick along in time and can advance through very, very, very many cycles within a second. And that allows you to subdivide the second into many small intervals and thereby measure time more precisely. And these optical clocks, they use ultracold atoms because we don't want the Doppler shifts from atoms flying all over the place. We want them to be fixed with respect to the laser beam that's probing them. And these have become extremely sensitive instruments. And here's an example of that. So this is coming from Szymon Kolkowicz, one of my colleagues at UC Berkeley, who has learned how to split a gas of cold atoms into several different locations inside of his vacuum chamber and measure time separately with each of these little dots of some, tens of thousands, whatever, of atoms. And the amazing thing is that these clocks, each set of atoms is a clock, it keeps time, but the clocks are separated by a few millimeters in height. And the gravitational redshift on the Earth's surface is now large enough that you can distinguish the rate at which these two objects are ticking time at a height of difference of just millimeters. It's really like a remarkably sensitive instrument. So we can measure time with extremely, extremely high precision. And okay, so when is this going to become the watch inside of my iPhone or something? Right now, the optical atomic clock looks like this, at least in Shimon's lab. It's technology that sits on two very big optical tables inside of a laboratory. If you open up those optical tables, you see a lot of instrumentation, a lot of optics. There's a lot of laser light going around. So this does not really look to anybody like technology, but in other hands, it is becoming quite miniaturized. So I was recently visiting the group of Katori out in Tokyo, and he's really taken on the task of trying to shrink these optical atomic clocks to instruments that are transportable. He wants to take optical atomic clocks and let's say, hitch them onto cars and drive them up to different heights so he can compare optical clocks at different heights on the surface of whatever, somewhere in Japan. And he can thereby, measure the relative heights of two locations and even see how those things are changing as, I don't know, plate tectonics happens or as, groundwater moves around or stuff like that. So this would be a really a widespread application. This thing called relativistic geodesy would be a widespread application of these optical clocks. There are other ways in which you use ultracold atoms as sensors. One of them is to use them as an interferometer that can measure things. So you know that light interferometers are used to measure various things very sensitively. For example, to measure gravity waves in the LIGO observatory, or to measure rotation. There's laser gyroscopes on the airplane that brought me here. So people are also building interferometers based on the propagation of matter waves. Pretty wild thing. And the way these work is the following. You get a gas of atoms and you get it to be spatially coherent. So maybe it's a Bose-Einstein condensate of atoms, or maybe it's just a bunch of atoms that have a very narrow velocity profile and therefore a very long spatial coherence length. Anyhow, you place these atoms in a vacuum chamber and then you zap them with light. So a typical thing is you put on a standing wave of light, and this standing wave of light causes some diffraction by the matter waves, by the atomic system in here. And as a result, the atoms that were initially, let's say, all in a zero momentum state, which was, I guess, indicated by this ellipse earlier, would now be in a momentum state where some of the atoms are recoiling up and some of the atoms are recoiling down after interacting with this laser light. And the interference between a wave of atoms going up and a wave of atoms going down gives you an intensity or a density modulation of the atoms. And that density modulation has its peaks and valleys at the same locations that the optical field does. So the atoms sort of acquire the pattern that light stamps on them. Okay, that's fine. Now you turn off the light and you let something happen. So for example, maybe you let the atoms fall under gravity. So the atoms fall, and now the pattern of interference inside of the matter wave is at a different location with respect to the laser beam that produced this interference pattern. And by zapping that laser beam on a second time, you can measure the relative position of the light intensity pattern versus the matter wave intensity pattern and measure this displacement, how far the atoms fell as a function of time. That's the way in which you can measure acceleration using a matter wave interferometer. And people are doing this. One of the things that people do is this is an experiment at Stanford University. They take a gas of atoms and they launch them, so they split them so there are two different wave packets, and the whole thing is flying up a 10-meter tower and flying down. The reason for having such a tall tower is to allow these atoms to undergo free fall for a very long time, several seconds. And then they go ahead and measure the relative population that are, let's say, moving up or down after a second interaction with these light fields. And in doing so, they can measure, for example, gravitational acceleration to a very high level, basically a part per trillion or something, a part in 10 to the 12. So these are becoming very, very sensitive instruments. People are talking about putting these up in space. That's an interesting topic as well. Now, not all interferometers have to be made of waves, because when I look at an ultra-cold gas of atoms, maybe I see something like an atom laser, a coherent collection or beam of atoms that looks kind of like a coherent beam of photons. And maybe therefore I should design matter wave interferometers so they look just like optical interferometers, like I'll just follow that analogy. But maybe I should think about interferometers differently. So for example, can I build an interferometer which is just based on quantum material that sits inside of a container? So we kind of developed this thought process. I was talking with Wolfgang Ketterle. We still interact quite a bit. Nir Navon at Yale, we've been working on this topic. But we just thought to ourselves, what if you built a different kind of interferometer where you take like a quantum fluid, a gas of atoms, could also work with other quantum fluids like helium or something, but imagine a gas of atoms and you divide it up into two containers, maybe somehow coherently. You split it into two containers, and now the quantum material over here and the quantum material over here, they're coherent with one another, and perhaps their relative phase is zero. Okay, great. So, but they're divided into two separate containers. And now take these containers and put them in different places. So, for example, what we were thinking about with Nir and Wolfgang at the time was take these containers and move them around in circles. That was in order to measure the sense, to use this material, these interferometer as a gyroscope. But anyhow, you put the containers under different conditions, and then you try to measure the relative phase that's been established between these two containers. And you can simply do it by pulling the two containers together and seeing, for example, if there's a Josephson current to the right or to the left. So that would be a different kind of interferometer that uses ultra-cold atoms, maybe thinking about them as a fluid rather than a wave. And this is an idea that's actually catching some momentum, haha. And here I'll point out recent work by my colleagues at Berkeley, Vicky Shu and Holger Mueller. Vicky is a new professor at Berkeley. Holger's been with us for some time. And what they're doing is using an optical cavity, see these two mirrors, in order to make a very spatially patterned standing wave of light. And then they take cold atoms, they place it in this standing wave of light, and with a bunch of pulses, they divide the cold atoms so that they now are trapped in this standing wave of light. Remember, I told you about these optical lattices earlier. They trap atoms within two different locations in this optical lattice, but it's the same atom. So an atom is basically split, so it is in a superposition of two different locations inside of this optical lattice trap. And because this trap and this trap are established by the same optical lattice, and that optical lattice is sort of fixed in a single spatial mode by these mirrors that form an optical cavity, then there's essentially nothing that disturbs the relative energy of the atom at these two locations, except for something, for example, like gravity, which would differentiate, the high energy and the low energy place where you've put your atoms. And the amazing thing is that they can now split these atoms into these two buckets, or atoms are now coherently placed in these two locations for as long as a minute. That's a long time. And they still remain quantum mechanically coherent. And this is going to lead to even better types of, even more sensitive interferometric sensors. So that's really amazing. There's a lot of things that are really amazing about atomic physics. And another recent amazing thing is this thing called the atom tweezer array. And I got my start in AMO physics at the point where there was a big revolutionary advance. All of a sudden, we could make quantum fluids made of cold atoms. We could make Bose-Einstein condensates and study their superfluidity. It was a really exciting time. That was like a big leap forward for the field. And we're experiencing another very big leap forward for the field, which is the atom tweezer array. So let me tell you what goes on in here. So to make an atom tweezer array, you take a beam of light and you split it so that it forms many different beams of light. This uses something called an acousto-optical deflector, but that doesn't matter too much. And then you focus these beams in. So you see these focused beams, they're inside of a vacuum chamber. And each of these beams is very tightly focused, so it has a maximum intensity at some well-defined location. And there's a whole series of these beams. Each of them is called a tweezer, an optical tweezer. And then you do laser cooling of atoms in the presence of these optical tweezers, and a really neat thing happens. Every once in a while, a single atom falls into one of these optical tweezers and stays there. Sometimes another atom falls into that optical tweezer, but those two atoms end up finding each other, and in the presence of the light that is doing the laser cooling, they quickly become a molecule, and both of them are ejected. So that at some point in your laser cooling, all of your tweezers that's shown up here will contain either one atom, just one atom, or no atoms. Those are the only two options. And since you're doing laser cooling on all these optical tweezers, you can collect the light that is emitted by these optical tweezers onto a camera. So these are images kind of similar to what I showed you on the first slide, where there's kind of two frames in the image. This is almost in real time. And in the first frame, there's 16 different tweezer locations, or the 16 different optical tweezers that we've imposed on a gas of atoms that's undergoing laser cooling. And you see in this line of 16 that sometimes, there it is, you see a dot. And sometimes along this line of atoms, you see holes, like, where atoms are missing. But because we can take an image and know where the tweezers are that are empty, we can get rid of them and then bring all the atoms that we know we have in the tweezer array into a perfectly well-defined array, where now we can prepare arrays of atoms with perfect filling and really any kind of geometric arrangement that we want. In the images that I'm showing here from my lab, we've only learned how to work with one-dimensional tweezer arrays. But in other laboratories, they're doing even more amazing things, where they place atoms in all sorts of arrangements, sometimes periodic, sometimes quasi-periodic. All sorts of things can be done. And the point is that you can now make a deterministically fully filled array of atoms with an enormous degree of control. But it doesn't stop there, because now you can also make these atoms interact with one another. So these atoms, they're trapped in optical tweezers, and they're typically a few microns away from one another, because the wavelength of light that you use to trap them is about 1 micron. So you need to be several wavelengths away to have different focused beams at different locations. So the atoms are a few microns away from one another, and at that distance, two neutral atoms don't really interact. They're neutral, they don't really have much interaction. But to make them interact, you can quickly excite them into Rydberg levels. These are levels of an atom where one of the electrons is excited to a really distant orbit. And now this electron that's very far from its nucleus can interact with another electron and another atom, and now there's a very strong atom-atom interaction. And with that atom-atom interaction, you can make strongly correlated quantum systems. This is, for one, a new frontier in quantum simulation. So, for example, there's this just completely amazing paper out of the Harvard group where they were able to use this technique to see magnetic spin liquids, basically in reality. Take a picture of a spin liquid and image it. And moreover, if you're willing to pay, I don't know, roughly $10, you can go onto this Amazon web server and you can use a commercially available Rydberg atom quantum simulator and run your own experiments. We tried that in my group and we had a lot of fun with that. So that's really a crazy development. But it gets even crazier than that, because this is not only the basis of a quantum simulator, but it's also the basis of a quantum computer. Because when you put two atoms near each other into Rydberg states, there's a way of making some conditional quantum logic occur, where, let's say, the state of this atom will be transitioned or transformed based on the state of this atom. And that's a 2-qubit gate, and it's therefore the essential building block of a quantum computer. And the idea of building a quantum computer using an array of atoms that are excited out to Rydberg levels has advanced extremely rapidly. So I don't know if you were paying attention, but just a few years ago, this paper came out, I guess 2023, actually. Anyhow. And this was like the spark. This is another one of these really revolutionary advances, where the group at Harvard University, led by Lukin, Vuletic, and Greiner, is able to demonstrate a quantum computing architecture. So they actually have an architecture for this thing called a quantum computer. And in this architecture, the things that are being operated on are not physical qubits, but logical qubits. So a set of physical qubits that together can encode a single quantum bit, but have the advantage that you can protect them against errors. This is such a run forward in the development of the quantum computer. It's a really striking thing. And I hope you've gone on to the supplemental materials for these papers and looked at some of the videos that they've put up, because here is a video of an algorithm that produces logical qubits and manipulates them. So every time atoms are moving around in this video from place to place, this acousto-optical deflector that I mentioned in the first slide is being driven with radio frequency fields that move these optical tweezers around, and the atoms move with them. And then every once in a while, pairs of atoms are brought near each other, and you see that little circle there indicates that at that point, the atoms are sort of zapped, and a quantum gate is affected between the two sets of atoms. And this motion is something that you can, in a university lab, orchestrate and run like a basic quantum algorithm with logical qubits. It's really an amazing thing, and it's developing extremely rapidly. So 2025 was really like a breakthrough year for the development of these neutral atom quantum computers. One of the really amazing results came out of my colleague Manuel Endres at Caltech, who showed that under a single microscope objective within that field of view, he could build up a processor that includes already thousands of perfectly identical qubits. In experiments separately at Harvard, people have gone these systems to where they're benefiting from quantum error correction. They're getting higher fidelity by protecting against errors. They're conducting actual algorithms using logical qubits. So, wow, this is really a game changer. And there's been a huge response to this, not just in the physics community, but also in industry. And by my count, there's at least 20 or so neutral atom quantum computing companies that have been established, including recently Google has also decided to jump in and bring neutral atoms into their quantum computing portfolio, because I think they're also realizing that this is perhaps the leading contender to building the quantum computer. There's a daunting amount of money being invested in this area, and innovations are being gobbled up by industry and being applied in industrial settings very rapidly. So it's a very exciting time. These optical tweezer arrays are going to impact not just the use of atoms for quantum computing, but really all applications of ultra-cold atoms. So now going back to the idea of a quantum sensor, there's beautiful research work, let's say in the group of Adam Kaufman at Gila in Colorado, where they build optical atomic clocks. And these clocks are based on atoms that are not trapped as previous experiments, kind of loosely in optical lattices, but atoms that are trapped tightly in these atom tweezer arrays. You can use them also as an optical clock. And one of the advantages is that in this way of building an optical clock, you can make use of these Rydberg excitations that I spoke of earlier, and you can turn this collection of atoms that are inside of your clock into some fancier many-body state, this thing called the GHZ state, which can measure time better than uncorrelated atoms. So it's like you have a optical clock where there's a set of control electronics, like the laser temperature controller and the laser current controller. There's a slot that's left open, and in this slot, you can now buy the entanglement generator. You can plop it in using the same techniques that you use for quantum computing, and you can now get more sensitivity out of your quantum sensor. So this is going to change how really all of atomic physics is done from now on. The atom tweezer array is going to change everything. Another thing that it's changing is the application of cold atoms toward networking and communications. So this is something that my group at Berkeley specializes in, where what we've learned to do is how to get a number of atoms, a counted number of atoms in a tweezer array to interact with single modes of the electromagnetic field with the idea that we can, for example, transform the many body states that we can create in this tweezer array, maybe using the techniques of quantum computation, and then turn them into optical fields by sort of activating the atoms optically, so that what comes out of here is a very interesting state of optics. So generating new quantum optical states by the fact that we have enormous control over atomic states. And we just got started on this. So for example, we've learned that if we take this array of single atoms and we cause them to emit light into the cavity, then depending on how the atoms are arrayed in this kind of metamaterial of atoms, they can have a collective response that is very different from the response of single atoms. So in this particular experiment from a couple of years ago, we learned how to make a set of atoms in optical tweezers either emit quadratically more light than single atoms would emit. This is a form of superradiance. Or we could also get them to emit very much less light than a set of single atoms by building up a certain correlation that is more related to subradiance. So there will be applications of cold atoms toward things like optical networking and optical communications, and that maybe uses tweezer arrays, just like everything else is going to be changed by these tweezer arrays. So great. So that's maybe somewhat convincing, but there's something that's pretty unconvincing, which is if you actually came into my lab to look at this really fancy technology that we've built that's supposed to revolutionize the world, what you would actually see is this god-awful collection of stuff. Lots and lots of optics, posts, breadboards. There's lots of cables that carry high levels of current. The actual experiment, you can hardly see inside of this space is where the atoms are actually cooled in this experiment and where the experiments happen. But all the rest of this support structure is really an overwhelming amount of stuff. And how do we get a robust technology out of this? How do we transform something that looks as messy as this kind of laboratory instrument to something that looks more like a reliable piece of electronics? How do we get there? And I would say that that poses what I would call a grand quantum engineering challenge. And I like to, when humanity had to build bridges, it established the field of civil engineering. And when it had to process information, it developed the field of computer engineering. So now we have a new challenge that humankind is facing, and that is how to control many body entangled quantum systems in a very robust manner. And that challenge can be taken on by engineers, and they can focus on two very big objectives. One is to engineer large-scale quantum systems that are that have long-lived coherence and entanglement. So there's approaches to that. And another big challenge that our engineers can come up with is to build the control systems. Look at all this stuff here. The control systems that are used to control these large-scale quantum systems. These are the two big goals that I kind of envision for a quantum engineering department. And what is needed in order to accomplish these goals is really a widespread effort. So what I'd like to see, not just in the United States, but elsewhere, let's say among the many fabulous science and engineering institutes here in India, is engagement by the engineering research community to work on the challenge of quantum engineering. This may necessitate kind of focused large-scale efforts to make this transition possible, and probably will be a really productive place for companies to start and for private investment to also move this forward. So I expect to see, and I hope to see, quantum engineering companies being established in the coming years as part of this quantum ecosystem that brings quantum technologies to a more useful state. So in terms of large efforts that are trying to build up, deliver on the promise of quantum information science, let me just conclude with a quick description of the Challenge Institute for Quantum Computation, which is this institute that I direct at UC Berkeley. So I'll just tell you briefly about the history of it. It's sort of a story out of American science policy. So a number of years ago, in 2018, there was a thing called the National Quantum Initiative. It was an act passed by the American Congress. And it said a lot of things. One of the things, it gave a command to the National Science Foundation to establish a bunch of quantum centers for research and for workforce development. And so, lo and behold, 5 of these centers were established. So the one that I established, that I direct, that's the CIQC. That's what I'll tell you about in the future, in the next few slides. But there's a few others that have been established to focus on quantum sensing, quantum networks, and quantum simulation. Hopefully, a few more will be established during this year. The CIQC, the one that I'm the director of, specifically is focused on the task of quantum computation. And it purposely brings together people from a really wide variety of backgrounds. So we have within our institute, we have chemists, computer scientists, engineers, material scientists, mathematicians, and physicists. We cover a really wide range of the stack of quantum computing, all the way from hardware to quantum computing algorithms, and also the breadth of quantum computing. So we have expertise in 3 different experimental approaches to quantum computing. And by bringing all these researchers together so that we, and in particular our students, all have a chance to interact with each other, we hope to make very new things happen. And the focus of the Research Institute is on these 3 long-term research challenges. So we hope to understand how to deliver, to realize the power of the quantum computer. So there's 2 elements to this. One is we still don't know the full range of what quantum computers are really good at. We know they're really great for quantum simulation, and as I pointed out, that's a really important topic. We know they're great at a few other tasks like, breaking codes, but we don't know all of what they can do. So we have to learn what they can do. And also we need to learn how to operate them. And there's really neat new ideas that are coming out on how to efficiently use the resources in a quantum computer to enable computations with really high fidelity. And then another challenge that the Institute takes on is how to actually build these quantum technologies, how to make use of innovations in quantum error correction or other architectures in order to build your computer smartly. But importantly, also to identify what are the critical resource bottlenecks that are coming up. And we have to be mindful because this is an academic institute with a budget of, I don't know, several $millions a year. That's a lot of money. But it's small compared to the billions of dollars a year that is going in through the private channels in investment into quantum computing companies. So we have to be really careful to focus on the longer term challenges where we think our small investment can have a long-term effect. And then last, we're really interested in science. And there's a lot of ways in which quantum information science, other than building up new technologies, is also giving us some really new perspectives on nature. And there's a lot of ways in which we understand physical systems different now by understanding, let's say, their capacity to store quantum information or transmit quantum information, from one place to the other. So that's the range of things that we work on in the Institute, and makes it a really kind of thriving intellectual space for me to have worked in the last few years of my career. So that brings me to the end. I hope I've sort of convinced you that ultracold atoms and molecules, maybe they will also be as useful, are a powerful tool for quantum science for sure, but also an emerging technology that may bring to fruition many of these dreams we have for what quantum technologies can do. And we think that they can empower a really wide range of the applications of quantum information science. But in order to get there, we really need a blitz of work, in particular in quantum engineering, to build systems that are more robust and adopt like an engineering mindset to make them work reliably. So that's all I wanted to tell you. Thanks very much for giving me the opportunity to speak with you.
Thanks a lot, Professor.
Yeah, thanks very much, Dan, for that wonderful overview. I mean, it gave a really bird's eye view of so many different topics. I guess, Gayatri, we are having a question answer session now, if that's okay with Dan.
Yeah.
Yes, I'm
Yeah.
happy to answer questions.
Yeah.
Uh, Maybe I'll just kick off with one question, which I was having during the talk, which is one hears about quantum sensing in the different context of, say, nitrogen vacancies and so on for detecting very tiny magnetic fields. Is there something in the ultra cold atom space would which would be comparable for the detection of magnetic fields in the high sort of precision measurements of magnetic fields?
Yeah, that's a fine question. So, atoms have definitely been used quite extensively as magnetic field sensors. So there's been a lot of work by many groups, for example, on atoms in vapor cells, so just room temperature vapor cells, and using them as very sensitive magnetometers. And there have been a lot of applications, let's say for like low field magnetic resonance imaging. If you can turns out with magnetic resonance imaging, if you measure the magnetic fields of precessing spins, not by inductance through a coil, but actually by directly measuring the magnetic field, then you can make measurements at lower precession frequencies or lower applied fields. And that has, some important technological applications. So there's been developments there. But one of the things that's special about the NV center is not that it's particularly sensitive to magnetic fields. Because in fact, I'd rather have an atom than an NV. The atom has a very, very long coherence time. The NV has a very short coherence time. So atoms are more powerful magnetic sensors. But one of the great things about the NV sensor is that it sits inside of a solid. It can be made at very, very high density if you wish. But more importantly, it can be brought very close to the object you're trying to measure. So that's, I think, was one of the really exciting developments of the NV sensor, that you have to put it underneath some layer of diamond to make it behave well. But maybe some fraction of a micron or something, you can have your sample on top of it, and that sample can be at room temperature, it can be at ambient pressure, and so forth. And that's not something that cold atoms give you quite the same. There's been a really nice set of experiments by Benjamin Lev out at Stanford trying to use cold atoms as a spatially resolved magnetometer of like a chip that sits below the atoms. And it's been effective. He's managed to get some nice experimental results out of it, but it looks really much more complicated than the NV sensor. So,
Okay, thanks.
yeah.
So we have a few questions here already. So the first question is from Modak. He's a BSc student, and for a BSc student aiming to go into quantum computing research, what balance should be maintained between physics, mathematics, and programming is his question. And what should be prioritized in the early years? Which branch of physics should be prioritized?
Okay, right. So you're asking, like, at the bachelor's level, what guidance do I have to your academic preparation that would qualify you to work in the area of quantum computing?
Exactly.
So I'm gonna admit that I have kind of a weird perspective on this, which is I think that you should study the basic topics that are before you. I think you should become have a really deep foundation in physics. And if you're also pursuing things like computer science, take a good foundation in computer science, learn about algorithms. I wouldn't worry at this point too much about taking coursework specifically in quantum computation or quantum information. And I say that because if I talk to the people that are going to hire you next, the people that are going to, let's say, you're going to work with maybe to pursue a graduate degree, or if I talk to people in the quantum industry who are employing people who are, coming out of schools, what they largely want is, well, two kinds of people. If I talk about the quantum industry, who do they want? Let me just ask that. In quantum industry, when you talk to them, they want two kinds of people. They want PhDs. Interestingly, they state that like a PhD is the most productive person they can hire into their companies. They're like, using a vacuum cleaner. They're just sucking up every PhD they can find. And so getting a PhD in a very basic subject related to quantum computing would be a pretty valuable direction. Or if not for PhDs, what they want is, let's say, a really great engineer. They want a really great electrical engineer or a really great computer programmer or a really great mechanical engineer. They want people who are trained actually in the conventional topics of academia, and then they will teach you everything you need to know about quantum computing. So I just want to kind of warn students against getting too worried about being too focused about preparing for this one future direction. I still think that a very generalized education with some familiarity with quantum computing and quantum information science, at least enough to get you excited about the field, is the right thing to do to prepare. I hope that answers the question.
Yes, sir. And I think we have one very similar question. And this person wants to go into atomic and AMO physics and quantum optics. So is your advice any different for them?
Yeah. So, again, as an undergraduate, just get a really great, solid overall background in, let's say you want to go into physics. You do a really great physics degree and study everything. Don't specialize too early. And one of the reasons is that, as I said, with this tree with all these branches, AMO physics is like the tool that you use to go in various directions. So you want to become that very creative person, after all, who learns how to take AMO systems and do new things in condensed matter physics, or as new sensors that can probe relativity, or as a quantum simulator that can, look at the physics of quantum field theories, or so forth. So I think you want a really great general base of physics. But it's also true that, let's say, to get into experimental work in AMO science, and let's say to move on to graduate school, it is becoming the case that having a research background, some level of research background, is pretty important. And it's important not because of the very specific skills that you acquire, because you can learn them in like a PhD program, but really because they provide evidence to the people that are going to supervise you for your PhD that you're good at research, that you're capable of entering a research lab, that you're capable of making this transition from being, I don't know, a passive learner who learns things through classrooms, to being a more active learner, a person who goes and gets the knowledge, reads the paper, derives the relations, and sort of understands things on their own. So I would say a good, solid, basic, basic understanding of your field, and then maybe some research experiences that allow you to kind of demonstrate how active and creative you can be in the lab.
Thank you, Professor. And we have another question from Darshan Rajesh. He asks, how exactly does an optical lattice work? Is the force that holds the atoms in place within the lattice due to the radiation pressure?
Yeah, good question. So it's not exactly radiation pressure that holds on to the atom. So radiation pressure, right, it's the scattering of light by an atom. An atom, basically, if it reflects or scatters light or something, it receives this photon pressure. That's not exactly what's going on. It's what's going on in an optical lattice is, well, there's two ways to think about it. One is it's the optical dipole energy, or the optical dipole force. So what happens is that, there's an energy there's an energy E dot D. Has units of energy, the dot product between the dipole moment of an object and the electric field it's exposed to. There's a minus sign up front. And a neutral atom does not on its own have a dipole moment, but when it's driven by light, driven coherently by light, it acquires a dipole moment, because in the presence of light, it actually is driven into a coherent superposition of ground and excited states. That dipole moment on the atom oscillates back and forth at the frequency of the optical drive. And it's that induced dipole moment dotted with the electric field that is the energy that's inside of an optical lattice. It's this thing called the AC Stark shift. And it's basically the electric dipole interaction due to the induced dipole itself. And for light that is red detuned from the atomic resonance, the orientation of the dipole moment with respect to the electric field gives you a negative energy. So by putting an atom in a red detuned optical field, you lower its energy. For a blue detuned optical excitation, the dipole responds out of phase to the drive of the electric field. Now the energy turns to be positive, and an atom raises its energy in the presence of light. That's what's happening inside of an optical lattice. So now if you make like an interference of two laser beams, you make an intensity pattern that's, dark, bright, dark, bright, dark, bright. Then if that's a red detuned lattice, the atoms will be attracted to the bright spots because that's where we lower their energy the most. And if it's a blue detuned optical lattice, the atoms will be attracted to the dark spots because that's where their energy is raised the least.
Okay, thank you, Vincent. So another question we have from Riddhi Chakrabarti. So they ask, your slide on resolving gravitational redshift at millimeter scales was striking. What is the actual limiting noise source at that precision? Is it quantum noise, thermal fluctuations, or something else entirely?
Yeah, great. So I agree with you. It's really stunning that people can see the gravitational redshift. The first measurements of the gravitational redshift were over very long distances. Actually, this really cool Mossbauer experiment over, I don't know, roughly the height of the building I'm in. The gravitational redshift between the ground and, things in orbit is pretty notable. Like if you didn't take it into account, your GPS system would not work. But the thought that you can measure the gravitational redshift over, the size of, I don't know, a coin or something, is really quite striking. It's a relative frequency difference, which I think is a part in 10 to the 20 or 10 to the 19. It's a really small shift in frequency overall. So what limits optical atomic clocks these days? That's a number of things. I don't I don't believe they're quite okay. So there is the atomic shot noise limit, right? So that comes from the fact that as you are looking, you have a bunch of atoms that are all after some pulses. There's an oscillation where the atoms are in the ground state versus the excited state for the ground state. And if you measure a population where you're half ground and half excited, that's the edge of a fringe, but there's a random choice of each atom to be in the ground or the excited level that leads to like Poisson fluctuations. That's the atomic shot noise effect that you're speaking of. And I I guess I'm guessing that the atomic clocks are actually limited by other things at this point. And one of them is there's systematic errors that are coming out. For example, the difference in energy between the atom in the ground state and the excited state turns out to be sensitive to the background black body radiation. So just the fluctuating electric field that's inside of the black body spectrum can sort of shift these energy levels somewhat. And if you don't know your temperature of the temperature of your chamber very precisely, then you don't know what that black body shift is, and that limits is one of the things that limits your clock. Another thing that can limit optical clocks is the laser that's probing the atoms, which has to remain, coherent over the time between, one operation and the next operation of your clock. So a lot of the people that are developing the optical clock are actually spending all of their time building very quiet lasers and very quiet laser cavities to do their thing. But for this comparison of clocks at different heights, that was one of the advantages that my colleague Shimon Kokowitz took advantage of. To some degree, a lot of these sources of error, the black body radiation shifts, and even the noise in the laser beam that's interrogating the atoms, those are common mode noises. So like in this set of optical clocks that are at different height, these two pieces of atomic gas that are a millimeter away from each other, they're all subject to the same overall shifts. And so if all you want to do is measure a frequency difference between them, you are immune from the overall shift in the frequencies. Anyhow, that's kind of what's going on in the optical clock system. But yeah, people are thinking about the fact that the atomic shot noise limit will be a limit. You can always find a regime where it is a limit, and that's where things like squeeze states or these GHZ superposition states, that's where they're supposed to come in and reduce the shot noise in your measurement. These are great questions. Thanks.
So we have a question from the YouTube live stream. It's from, so can one look at the response function of an atomic cloud when one perturbs with the magnetic field and use that in developing magnetometry? Yes.
Look at the response function of an atom in a magnetic field. So I'm not really quite sure what is implied there. I mean, I will tell you that the most sensitive magnetic field sensors, make use of the fact that in the ground state of an atom, you have spin states or angular momentum states of the atom, and those different states can have an energy separation that depends on the magnetic field. And you like to work with those low energy ground states of the atom because they're basically infinitely long lived, so you get very long coherences. So you can place the atoms in superpositions of, let's say, these spin states, wait a while, and then check on that superposition, and that measures the strength of the magnetic field that's been applied. Now, there's the question, how do you make that measurement, after all, of the coherence between two spin states? There are, for example, optical methods for measuring that, where you make use of some kind of anisotropic optical response. So I'm getting back to response function, which was in the question. You measure some kind of anisotropic response where maybe the interaction of an atom with a particular polarization of light depends on the orientation of the atomic magnetic moment. And then you can sort of make the signal of your magnetometer show up on an optical beam, and that helps you read out what's going on in the atomic system.
Thanks, Professor. And we have a few questions from Raghav, and I'll read out two of them. So he asks, one is, how does quantum sensor work? And how do ultra cold atoms behave? Is one of the few questions that he has asked.
Okay, I'm going to try to put those two questions together, try to answer how quantum sensors work, and then maybe try to say, why is it helpful that the atoms are ultra cold in these sensors? Maybe that's the way I'll interpret the question. So how does a quantum sensor work? Boy, that's a really, really big topic. At base, the most basic, I mean, I gave a couple of examples, but at base, your atom is a quantum system, and it has different energy states, and those energies can be sensitive to something. They can be sensitive to applied magnetic fields, or they can be sensitive to gravity in the form of acceleration. They're sensitive to electric fields. They can also have an energy separation that is just a fact of life, and that energy separation is maybe something you just want to measure, let's say, to determine time. So you have an atom, it has quantum levels, and there's energy separations between them, and then you need to make a measurement that's sensitive to that energy difference. And the common way of doing that is to take the atom and place it in a superposition of these two energy levels. And because of the energy separation between the two levels, there's a phase between the two parts of this atomic wave function. And that phase advances in time, like omega, which is the energy divided by h bar, omega times the time. There's an advancing phase. And then you measure that phase, the phase of that evolution. And there's ways to do that by, applying another pulse to the atom so that the population that ends up in one of these two states at the end of that last pulse depends on the phase, and from that you measure the frequency that you're interested in. And great, so that's one way in which quantum sensors work, is you take a quantum object, you place it in a superposition, you let that superposition evolve for a while, and you check on it. And from that, you gain information on whatever is going on. And why ultracold atoms are useful for that is that they're very slow. So there's no Doppler shifts. That's very helpful. They're very cold, and that means that you can trap them using a field which itself doesn't screw up the sensor. So the fact that we can take the atoms in Shimon-Kolkowitz's optical clock and we can trap them in a very low intensity optical lattice is really good, because it means that there isn't a disruption of these optical clocks by the light that's just holding on to the atoms at those different locations. So that's one of the ways in which we gain. Now, I was saying that the question of how a quantum sensor operates is actually a complicated question, because there's a lot of really exciting new theoretical ideas that are coming out for what exactly a sensor is and how do you learn from the physics of a quantum system. So there's one topic, which is something people called Hamiltonian learning. So if you have a system that behaves according to a Hamiltonian, this which defines the energies in a system, how should you let the system evolve in time and then measure its state so that you can learn what those terms are in the Hamiltonian? That's something called Hamiltonian learning. And Hamiltonian learning is basically quantum sensing, because the terms in the Hamiltonian maybe are the things that you want to sense. Maybe there's a magnetic field that changes energy levels, or maybe there's a magnetic field that changes an interaction energy. So it's like a two-body operator, and you want to measure that really well. So it becomes like an information theoretical idea, like what's the best way to make use of the resource that you have, which is a quantum system that evolves in time, in order to determine these quantities within the Hamiltonian. And a really radical new concept is coming up, something that is being called quantum computational sensing. And the idea is, the old way of running a quantum sensor is to get a sensor, operate it, get a reading, write it down on a sheet of paper, and then do it again, and do it again, do it again. Now you have all these numbers on your paper, and you do some kind of averaging to get like a better overall measurement, because you can average many measurements together. In a quantum computational sensor, you do something different. You take the quantum sensor, and at the end of the sensing protocol, you take its state and you store it. And then you do it again, and you take the next state and you store it. And you store all the quantum states of the sensors. And then using a quantum computer, you process all that information. And there's a way in which you can actually extract more information, because a quantum computer has acted on this data than the classical computer would have acted on classical data. Isn't that a neat idea? So that one of the biggest applications of a quantum computer might be just to operate a better sensor. And maybe that better sensor, I don't know, discovers something new about the universe. That would be a really neat outcome to the entire quantum information game.
Fantastic. I had another question, which is I was asking Anna Maria yesterday about in her talk at ICTS about these nuclear clocks that people have been talking about recently. But in the context of your talk, I want to ask whether the nuclei of these cold atoms are there aspects of the I mean, can one exploit the, I don't know, the nuclear magnetic moments and other couplings and other or maybe even I realize that nuclear energy transitions are, of course, MeV typically, and not of the same, the electron volts of the atomic transitions. So maybe, except maybe some funny examples like this thorium case for nuclear clocks. But are there some other aspects? Once you have this very cold atom, you also, of course, have the nucleus there, very heavy nucleus. Can you do something with it, or are people doing things with it?
Yeah, so I'm not a big expert in that, but there are people thinking about, for example, efforts to measure electric dipole moments of fundamental particles. So, right, so this is, a topic in fundamental physics. We ask whether the fundamental particles that we have on hand, for example, the electron, but also things like the neutron, whatever, whether they have not just a net charge, like the electron, proton, and neutron do, but whether they also have structure that would give them a net dipole moment, like a difference between the location of positive and negative charge. And that the standard model of physics predicts that particles will have electric dipole moments, but ones that are very, very, very small. And then extensions beyond the standard model that are maybe posited to explain some of the aesthetic conundrums of high energy physics, they might lead to larger values of the electric dipole moment. So the effort to measure electric dipole moments of fundamental particles is a really important direction for precision measurement. And ultra-cold atoms can play a role, and ultra-cold molecules can play a role in those experiments as well. Because EDM or electric dipole moment measurements are kind of like magnetometry. You try to measure something like an effective magnetic field that's actually created by the fact that you apply a large electric field. So everything we just talked about how magnetometers operate, is exactly how searches for the electric dipole moment operate. And we think that if you can trap a variety of atoms, but it's even more valuable to trap a variety of molecules where within them there's a high sensitivity to this electric dipole moment of fundamental particles. That might be the thing that allows us to make these fundamental discoveries, maybe, and see something that's outside of the standard model of physics. There have been a number of experiments, actually, my predecessors at Berkeley, Eugene Cummins, had a long research program trying to measure the electronic and nuclear EDMs using atoms. And that moved along pretty far, but I'd say those searches are now being surpassed by ones that make use of make use of molecules, where there's subtle things about what goes on inside of a molecule that makes it more sensitive to these effects. And one of the drivers for making ultra cold molecules and not just atoms is to use them in these kinds of EDM searching instruments. So, there may be a pretty big breakthrough in the next few years or whatever decade that uses, I don't know, dipolar molecules in an optical lattice or something, maybe with entanglement generated by Rydberg states or something, that finally finds a mistake in the standard model. Or maybe not, maybe there's no errors and we'll still find just lots of zeros, but it's worth checking.
Absolutely. Thanks.
We're almost, I think, out of time. So if it is okay with you, Professor, we'll take one more question and then we'll close the question answer session.
Sure.
Yeah. So this question asks, after quantum research attains saturation, would momentum shift over to matter that does not interact with light? Maybe dark matter computation, as quantum computers would have unearthed the mystery of dark matter by then, is what they ask.
Wow, that's a really exciting future. I have no idea. I just have no idea. Yeah, that was an easy question to answer because I really have no idea. But I think we can dream big. Whatever, 95% of the universe is something we don't even know yet. So, all of you folks who are interested in studying, fundamental physics and dedicating your careers to that vast unknown, you may be able to make, really earth-shattering discoveries. And, it's always happens. You make some kind of fundamental discovery, and then sometime later it turns into essential technology. When people discovered the Maxwell equations, they weren't thinking about as widespread use as we have today. And people who first invented or discovered quantum mechanics were not thinking already about the quantum technologies that we're trying to develop 100 years later, but it did start with their effort. So I don't know, somebody's going to figure out, I don't know, dark matter is made of whatever it's made of. And I don't know, 100 years later, is there like dark matter technologies? Maybe. Maybe. I mean, there's history has there's a lot of history coming up, and I don't know where it's going to go.
Thanks a lot, Professor.
Okay. All right. Well, thanks.
Yeah. Thank you, Professor Dan, for giving us such an enlightening talk. Thanks a lot, everyone, for joining us. So we'll slowly wind up the talk now.
Okay,
Thanks
great.
again.
Thanks. Bye-bye.
All right, so I'll log out.
Yeah,
Oh,
yeah, Professor.
Okay, great. Well, that was fun. Thanks
Yeah.
everybody for really fun questions. I love the last question. That was really a good one to end with. And yeah, no, for real. I mean, there's discoveries to be made out there, and so it's exciting, exciting future. Yeah. All right, I'm gonna log out.
Thank you. Thank you,
Bye.
Professor. Thank you.